All right, we're going to continue going over your review, starting with the AP questions. So these are ones that have been shown on previous AP exams. So here we go. Here we have and they are all the multiple choice ones. So we've got this vehicles that are driving more than 5 miles over the speed limit, 40% of them. Okay. Now, they said out of 4 randomly selected cars, so that's a set number. So we have a binomial situation here. What's the probability that at least one of those vehicles or drivers is speeding more than 5 miles over the speed limit? So that's your probability of at least one. So this one is that because it's at least one of the successes that we're looking at. So that's probability that none of the 4 motorists are going over the speed limit. 1 minus probability that all are not speeding. So in order for all 4 of them to not be speeding, that would have had to been the 60% to the 4th power. So there is our 0.8704. Now here we have been given some information, okay? And so we've been given the total foreign language and the total psychology, all right? So, and then we have what this or that is. So that means the combined total for those 2 circles was 32%. The problem is that if you added your 28 plus 17, that's more than 32%. Okay. In fact, how much is that? 45%. Okay. So because of that, we can then see that this is the area that gets double counted. So you know that when we would do our formula, it would for this or that, it's the probability of the foreign language plus the total probability for psychology minus the overlap. And that's what we are looking for. How many are involved in, or what is the probability that a student is in both foreign language and psychology? That is the overlap. So we did the total foreign language plus the total psychology minus the overlap. And then I solved. Oh, it's 13. Okay. All right. So there, yeah. So there's that because that was 45. And then that overlap was 13. So 13%. Oh, hold on a second. Yeah, because this was in percents. It wasn't out of a number of items. Okay. Next, here we had these 6-sided die, and we were talking about the sum of them. So what's the probability that the sum will be 4? So you have to think of the ways you can get a sum of 4. And so that's what I have. I showed this chart here just so you could kind of visualize what's happening when we have all of our die, and we have 1, 2, 3, 4, 5, 6 for one die, and 1, 2, 3, 4, 5, 6 for the other. And then these numbers in the middle are the sums. So see, like this is 1 plus 1 is 2. 2 plus 1 is 3, and so on. So the question asks, what's the probability we have a sum of 4? Well, there are 3 ways to have a sum of 4. Okay. However, it says given that the sum is less than or equal to 6. So we had to then also see what is this pink area. These are all the ways that the sum is less than or equal to 6. And so that turned out to be, what is that, 5 plus 4, 9, 10, 11, 12, 13, 14, 15. So those 15 ways. So 3 ways to get sum of 4 out of the 15 ways there. Okay, so that's how we came up with our 3 out of 15. All right, moving on. So here we had this was a very important fact that eye color and gender are independent. So what that told me is that the males and the females have brown eyes at the same rate. So of the 80 males, 60 had brown. So then I can tell, okay, then that means 75% of the males had brown eyes. And because eye color and gender are independent, the females have the same rate. So I just need to do 75% of the females. So I had to find out how many females we had. um, 80 were male. So if 80 were male, then 120 were females. So that's 75% of the 120. And that's how you get your 90. All right. So here we had this situation, seeing, you know, we had basically seeing if you know the definition. So in this one fell swoop, this one problem, we saw if you knew the definition of mutually exclusive and independent. Mutually exclusive is the same thing as disjoint. Disjoint events cannot happen at the same time. Mutually exclusive of each other, separate. So that means that because so I can tell you that right there. Look, the probability of being awarded both jobs, that's events A and B together. So you can be awarded both jobs. So at that point, I already know mutually exclusive is out because you can have overlap. So they are not mutually exclusive. So here I am with, I got C, D, or E. Now I need to see, are they independent? Okay. So you know our big deal on that. So probability of A and the probability of A given B. So then I just did the math on that, and I found that, look, probability of A is the same as probability of A given B, so they are independent. And so that means that that gave us answer choice C. Now, FYI, we do know, and this is kind of like a side product, if they were independent, then I should be able to multiply event A times event B and get event A and B together. So, probably a quick way that I could have done that is said, okay, I'm just going to multiply 0.75 times 0.5 and see if it equals 0.375, and it does. So then therefore I know that they are independent. Okay, so there's another way. All right, now here we want to know the probability that a household owns a cat or a dog. Now we are told the total probability, the total proportion of households that own a dog, 36.5%, and the total proportion of cat or households that own a cat, and that was 30.4%. Okay, so we have the totals for each one of those categories, but I know that there are some houses that have cat and a dog. So what happens is if I just added the 0.365 plus the 0.304, then those people who owned a cat and a dog, those households would get double counted. They would be in the dog total and in the cat total, so they got double counted. Therefore, since they do not give me that information to be able to subtract away the part that gets double counted, then I do not have enough information for this. Okay? All right. And the next one. So, this problem, I did it so hard. I went through a whole lot of all this thought process, and then I was like, oh, well, that just seems weird. And I mean, what I did was right, but it was so much harder than another way. So, anyway, so I didn't completely take away all my work because some people might have thought about that. So, I'm just going to leave this here because this takes like a lot of thinking. And I don't have common sense. So this is typically a way I go at things. So I kind of have had to learn to mimic common sense from my students. But anyway, here we go. So what we know is that if device A, B, or C, if any of those three fail, then if parts A, B, or C fail, then if any of them fails, then the whole device fails. So what I was thinking, the way I went wrong in my really hard thinking was I was like, okay, well, so if at least one of those A, B, or C fails, okay, then I know that um, the whole device is going to fail. So let's see. For the device to not fail, then so the way that there's only one way that the device doesn't fail. And it's if all three of those components are successful. Because if any of them are bad, then the whole device fails. Okay. So that's really actually the easiest way to go at it. So in order for the device to not fail, A has to be successful and B has to be successful and C has to be successful all at the same time. So then over here on the side, they told me the failing probability. So I said, okay, well, that means 99% of the time A is successful and 97% of the time B is successful and 96% of the time C is successful. So if I multiply those three things together, because I want A successful and B successful and C successful, then that's the probability that the device will succeed. Okay, the only one way that the device does not fail. So there it is. And if you want to study this other part, go for it. But it's way too hard. Okay, number 24. So let's see here. Okay, so it took me a while in reading this to kind of see. I think at first when I read this, I thought I was going to do a tree diagram. But then I kind of sorted through what it was talking about. And so the probability of stopping is 0.05. The probability of being damaged is 0.10. And then they told me the overlapping part, the stopping and damaged, is 0.04. So I have, the total for part A and the total for part B, and then the overlap of A and B, if you want to think about those events. So the question says, given that the new microwave was damaged during delivery, so see, that's this, given that it was damaged during delivery. So the total damaged during delivery goes on the bottom, and that's that 0.10. Then what's the probability that it also stops working in less than 2 years? So then that's the overlap, because what goes on top is the overlap of stops working and being damaged. So that's your 0.04. So if it's damaged, so that's interesting. If it's damaged during delivery, then there's a 40% chance that it's going to stop working within the next 2 years. Okay, so I might raise a little stink about that. All right, and here we have a weighted average problem. So this was actually pretty involved, however. So let's take a look at it. So we have the total subscription, and then it's broken down by men and women because the men and women read advertisements at different rates. So in hindsight, I wonder if this could have been done like a tree diagram. Anyway, so I guess, so I don't know. You could have probably done it that way too. All right, but I thought of it this way: 30% of the 640,000 women will read it, and 50,000 or 50% of the 980. So 682 then is the total who are going to read it. Okay, so then I just need to find the percent, and the percent's going to be the part who read it out of the total. So then that's how I got that part over the whole. So that was 42.1%. Now then it said in a random sample of 100. So what if it had not said 100? What if it had said in a random sample of 200? How many do you expect to read it? So once you get that percent, then you would need to multiply it by whatever size sample that is. Ooh, that would have been really tricky. They added that third component to you to do. All right, now we have 2 free responses. So here we go. So these were actual AP questions. 2018 was number 3, this one right here. Okay, we had multiple conditional probabilities. We had multiple bursts and single bursts happening in this area, and then the rate at which they were lefties or righties. Okay, so then the question just says, what's the probability that a randomly selected child born in the region is left-handed? So that's after I do this. So that's going to be my total left-handed, the 0.007 for the multiple births, plus the left-handed for the single births. So I'm going to add those 2 together. And that actually is important to get that answer because it ends up being used in the next parts completely. Okay, an interesting AP fact: if you can't figure out part A and it needs to be used in the subsequent parts, you could make up a reasonable answer in part A, and you will miss part A. But if you use it correctly in parts B and C, then you can get full credit for parts B and C. All right, so here we go. What's the probability that a randomly selected child born from the region that is multiple birth, given that the child is left-handed? So see, that's going to use that probability from part A. So that's the total, and then the part that's from multiple births is on top. So actually just 6.76% chance that they were from the multiple births if we know that they were left-handed. Okay? All right, now here we go. Last part, a random sample of 20. That is a set N. Okay? So what's the probability that the sample will have at least 3? So I want from 3 up to 20 successes who are left-handed. And so that means I want 20, choose 3 successes, up to, in the sequence, 20, choose 20. And look here. Look at this. The probability of left-handed was used again. So this came from part A. So once again, you had to know what it was that you found in part A to be able to do that there. Okay. So then we did that. And then remember, if I want the upper part, then I have to do 1 minus the lower part. So 1 minus the accumulation of 20.1139, and I want to take off the bottom 2 and below, so that what remains is 3 and above. All right, next is the last one. It's a 2011. So we had upgrades on flights. And so we first wanted to know what's the probability it's going to happen. Oh, Oh, look, it says will occur after the third flight. So I did this wrong because I did what's the probability that it's going to occur on the third flight. So I need to fix that. So let's just kind of talk through that. I totally didn't see, or I just skipped. I was so tired by this point. After the third flight. So that means the successes. So the successes that I want on the fourth, up to infinity. Okay, so I think so. Then I'm going to have to do 1 minus the bottom part, the accumulation of successes on the bottom part, or if the first success that occurs after the third, so the first success occurs in that fourth spot, then another way of thinking about that is it's saying, okay, if the first success occurs in the fourth spot, then the first 3, so whatever happens, I just know the first 3 are not successes. So technically, we could just really say, oh, okay, then I just need to go, what's the not success? So 0.9 to the third power, because all I know is that the first 3 are not a success. And then you get whatever that is. Okay, so I had messed up on that one. All right, and we'll fix that. Okay, I'll have to update that in the answer key that I put online. So here we go. Okay, the next one. What's the probability exactly 2 times? Okay, so this one was an exactly. So there was, now it's, but it's exactly out of the 20 flights. So 20, choose 2. Okay, but now here's where we get it interesting. He takes 104 flights, so that's our N. Okay. Would you be surprised if he receives more than 20? So that means I'm thinking, would I be surprised if more than 20, so that's 21 and up, is an outlier? So there's 2 ways you can think of this. The first one is compute the mean and the standard deviation and then see if 20 is an outlier. Either way, you have to do the mean and standard deviation. So I did that. There's the mean and there's the standard deviation. And 21 is actually just inside that fence. So 21 wouldn't surprise me, but 22 or more would. So the point, you have to, recognize that 21 is not unusual. So that was important that you said 21 is not unusual. Now, and then you did or did not have to say 22 or more would be. Okay? Cuz you're always going to if you're going to infinity, you're going to reach a point that is unusual. But the point is 21 is not unusual. So look, here's the other one. And you don't actually quite know this yet until we get to inference next semester. So that's why I thought of this as option 2, because you might not have thought of it this way, but you might could have, and that's fine, because we have talked about this type of thing where, when you have the normal model, what how much percent is in above the how much percent is above 2 standard deviations? Well, 2.5% is the top part. So if your probability is somewhere up there, so less than 2.5%, it's unusual. If it's greater than 2.5%, then that means you are over here inside the fence and that there's something that's a little bit more probable. So that's another way you can do this. So I did the binomial from 21 up to 140. And so I took off the bottom 20 and see, look, I got 3.92. And so that is not less than 2.5%. So therefore, it's not considered unusual. Okay, and so that's why I would say that I would compare it to that 2.5%. What that tells me is that that slice of 21 is probably the most of the highest portion of this probability outside here. Okay, the part above that 2.5%. Okay, 1.42. All right, so that's it. I think that was all of our questions that we had on our review. A lot of good stuff, a lot of hard thinking on that. So I hope that you understood most of that and that you were well prepared for your test.